Hello everyone. So in this video, we'll be discussing strength of materials. So first, let's define what is strength of materials. Strength of materials said to be dealing with the relations or the relationship between the external forces applied to elastic bodies and the resulting deformations and stresses. In the design of structures and machines, the application of the principles of strength of materials is necessary if satisfactory materials are to be utilized and adequate proportions obtained to resist functional forces. So, under strength of materials, we'll be discussing stress and strains or the deformation of some applicable object or body. So, let's discuss first the analysis of internal forces. So, we have axial force. This is the component measures the pulling or pushing action perpendicular to the section. Under axial force, we have tensile force, compressive force. Tensile is the pulling of the object. So, for example, we have here an object and we have application of force that is that is like giving tension to our object. The compressive force naman is just like pushing the object to compress, and force is perpendicular to the contact area. We also have what we call the shear forces. These are components of the total resistance to sliding the portion to one side of the exploratory section past the other. We also have torque. It measures the resistance to twisting the member, or this is the twisting of some objects. That is what we call torque. And the bending moments, which measures the resistance to bending the member. For the elastic properties, this is just an overview of the strain or the elastic modulus, which is said to be equivalent to stress over strain. So from the graph here, you can see that at this point, our object will obtain its breaking point. So meaning to say, past this point, will our object will already break. So the elastic limit, this is the elastic limit, and we have the elastic behavior. This is the capacity of our object to elongate. So again, in this video, we'll be discussing stress and strain and some applicable examples for stress and strain. Stress is related to the force causing the deformation. Strain naman is a measure of the degree of deformation. The elastic modulus is the constant of proportionality between stress and strain. So first, let's focus on discussing stress. So stress is when a force is transmitted through a body, the body tends to change its shape or deform. The body is said to be strained. Intensity of the internal force measured by force per unit area. So the stress formula is given to be equivalent to force over area. And please note that this is the symbol of the stress, and that is equivalent to the force over area, which is N over M squared. N over M squared is basically equivalent to Pascal or the PA. So that is the unit of our stress, Pascal. Stress is also defined as the strength of material per unit area or unit strength. It is the force on a member divided by area, which carries the force formerly expressed in psi. Now it's expressed in N per mm squared. If it's mm squared, that is equivalent to megapascal. But if it's N per m squared, that is just equivalent to Pascal. And again, we have the formula stress is equal to force over area, where P here is the applied normal load or the force in Newton, and the A here is the area, and that is in millimeter squared. And you can also change, or you can also use meter squared for the area. It just depends on you. We have different types of stresses. We have first is the simple stress. The stress within an object can be described by a single number or by a single vector, a number and a direction. So we have the normal stress, shear stress, bearing stresses, thin-walled pressure vessel. These are under the simple stress. So now let's discuss what is direct or normal stress. So direct stress may be tensile or compressive and result from forces acting perpendicular to the plane of the cross-section. So kung pabira ang ato ang force or pagawas sa atong object, that is what we call tension. But if the force is compressing our object, that is what we call compression. And the area is this one, the area of our object. That is again given by the formula stress is equal to P over A or F over A, where F or P are the loads or the forces acting on the object, and A is the area. For example, we have here a steel wire 10-meter long and 2 mm in diameter is attached to the ceiling, and a 200 Newton weight is attached to the end. What is the applied stress? So from the formula of the stress, we have stress is equal to F over A or P over A. So from here, the applicable force is 200 Newton, and our steel wire is 10-meter long and 2 mm in diameter. So if we would draw that one, we can say that this is the ceiling and we have our 10 mm long wire, steel wire that is attached to the ceiling, and we have the weight that is attached to the end of the steel wire. So let's say this is our weight or the force acting to our wire, which is 200 Newton. So we can just basically easily substitute here the 200 Newton over our area. So the area that we are looking for here is the area of the steel wire. If you can recall, steel wire is circular. Steel wire is something like this. So we are looking for, or we'll be using the area for the circle. So since we have a given diameter here, that is for the area of the circle in diameter, that is just basically equivalent to pi over 4 d for the diameter, but it's in mm. So we can also change that one into millimeter by dividing that by 1000. That is squared. So the stress is now equivalent to 6.37 times 10 raised to negative 5 Pascal. So this is now the allowable stress, or this is the applied stress. Next example we have here, the elastic limit for steel wire is 2.48 times 10 raised to 8 Pascal. What is the maximum weight that can be supported without exceeding the elastic limit? So again, the elastic limit is here is the stress for the steel wire. So that gives us 2.48 times 10 raised to 8 Pascal. And as you can also see, Pascal is the unit, so that is stress. And we are looking for the force that can be supported without exceeding the elastic limit. So in order for us to solve for this one, as we all know, stress is equivalent to force over area. And since we are looking for the force is just equivalent to stress times the area. So that being said, F is equivalent to 2.48 times 10 raised to 8. And again, that is steel wire, so the area for that one is the area that this example is connected to the last example. So the area for here, if we would calculate the area, this is equivalent to This is our area. So basically, the area is just equivalent to 3.14 times 10 raised to negative 6 meters squared. So this is then equivalent to 778.72 Newton. This is the force or the weight that can be supported without exceeding the elastic limit. Therefore, beyond the number or beyond the force, beyond 778.72 Newton, the wire would already break. Next example, we have a hollow steel tube with an inside diameter of 100 millimeter. So the diameter of the inside is 100 millimeter, must carry a tensile load of 400 kilonewton. So if this is the wire, this would carry a tensile load of 400 kilonewton. Determine the outside diameter of the tube if the stress is limited to 120 mega Newton per meter squared or megapascal. So in this case, let's just identify first what are the given. So the inside diameter again is di is 100 millimeter. You can also convert that one into meter, so that is 0.1 in meter. And we also have the tensile load or the force, which is 400 times 10 raised to 3 Newton. And the stress is limited to 120 times 10 raised to 6 Pascal. Okay, so we are looking for the outside diameter, or we are looking for the D, the bigger D. So in order for us to solve for that one, we need to solve first for we can solve for the area. So as we know, the area that we'll be using is the circular area, or the area of the circle, which is, since we are dealing with diameter, again, we'll be using pi over 4. And then we will be subtracting the bigger diameter minus the smaller diameter or the inside diameter. So we have D as our outside diameter minus the inner diameter, which is 0.1 in meter. So we have 0.1 squared. So this is our area. Now, we can substitute that to our equation so we can find the value of our D. So the equation is looking for that stress is equal to F over A. So let's just interchange this one. So we have A is equivalent to F over stress. And A is pi over 4 D squared. Sorry, this should be D squared minus 0.1 squared is equivalent to the force, which is 400 times 10 cube Newton, divided by our stress, which is 120 times 10 raised to 6 Pascal. So if you try to shift solve this one in your calculator, our D is equivalent to 0.11935 in meter, or that is equivalent to 119.35 in millimeter. So either way, either of your unit or either of the answer, depending on the unit, is still correct. The next one is normal or actual stress. Normal stress is either tensile stress or compressive stress. So this is just basically the same with what we have discussed from the previous slide. Member subject to pure tension or tensile force is under tensile stress, while compression members subject to compressive force are under compressive stress. So this is an example of the bar in tension. So there's forces that are pulling the the object, whereas in compression there is a force that is compressing the object. So compressive force will tend to shorten the member. So if you can notice, if you push this one, if there's force applying to the bar or to our object, our object will tend to shorten. And for the tension naman, it's just like pulling a an elastic rubber band, so it would also elongate. So for example, a 5 mm diameter of cylindrical bar is subjected to a tensile load of 4 kilonewton. Find the stress. So we have here again, this is still one of the basic example. We have stress is equal to F over A, where F is 4 times 10 cube Newton over our area, which is in diameter. So that's pi over 4. Let's just use meter, so we can have that in Pascal. So that's d squared. So basically, stress is just equivalent to 203.72 times 10 raised to 6, or this is in megapascal. This is now our stress. Okay, so another example we have here, determine the largest weight, W, that can be supported by two wires shown in the figure. The stress in either wire is not to exceed 30 megapascal. The cross-sectional diameter of wires AB and AC are 0.4 centimeter and 0.5 centimeter respectively. So we have here these wires, and the diameter for the AB for this wire is 0.4 centimeter, and the diameter of this wire is 0.5 centimeters. So we are looking for the safest load that can be supported by these two wires. When we say the safest load, that is the smallest load that the two wires can carry. So if we translate this figure here into a vector analysis, we can have this as AB. This is the AB. This line is the AB. And it says that this has an angle of 30 degrees here. And if you also translate this one into the vector analysis, we have this as this is AB, this is AC. Okay, and the weight that we are looking for is from here. So we are looking for the weight. Okay, and if you can notice again, this one, the angle for this one is 50 from here. So that's 50 degrees. So now we are looking again for the W, or the safest value for the weight, so that it can be supported by the wires B and C. First, we are going to identify the values that we have. We have the stress is not to exceed 30 megapascal. So our stress is equivalent to 30 megapascal. We have the diameter for AB is 0.4 centimeter. And the diameter for the AC is 0.5 centimeter. Now, as you can see, this is now the basis of our solving or our solution. We'll be looking the value for the W, possible value for the W. So from here, we can use sine law from here in order for us to solve for the W. So this is tension AB, this is the AC. We can say that TAB over its angle, the opposite angle of TAB, which is this angle, the opposite angle of TAB is this one. So if this is 50, this is 50 degrees here. 90 degrees minus 50 is 40 degrees. So meaning to say the angle here is 40 degrees. So that gives us sine 40 degrees, which is equivalent to W this side and the sine of the angle opposite to it. So if this is 50 or if this is 30, and since this is right triangle, so meaning to say in order for it to have a 90 degrees angle, this is 60 degrees here. And if this is 60 degrees here, meaning to say this one also is 30 degrees. So 50 plus 30, that is sine 80 degrees. Now we can just cross multiply this. We have TAB is equivalent, is TAB sine 80 is equivalent to W sine 40. Again, we are looking for the W. For the T here, this is what we call the tensile force or tension. So that is also equivalent to the force. So meaning to say force in stress, that is equivalent to stress times area. So that means our T here can be replaced by stress times area. Sine 80 degrees is equivalent to W sine 40. So our stress is given here, 30 times 10 raised to 6. And the area is this is for AB, so this is pi over 4 of 0.4. That is in centimeters, so we'll be dividing that one to 100. So that will be translating this into meter. Okay, so this is in squared and the sine 80. And since we are looking for the W, we'll be dividing both sides by sine 40. So in this case, the W here is equivalent to 579.13 Newton. So meaning to say that the wire AB can support until 579.13 Newton of weight. Now let's also check how much TAC or the AC wire can be supported. So we also be needing to use the same formula. So we have TAC. So we're looking for this one. So it's a little messed up already. So TAC, so we are looking for the opposite angle. So that is this one, this side. So that means TAC is equal over sine 60. That is equivalent to W over the opposite angle, which is 80. So the same goes here. We have TAC sine 80 is equivalent to W sine 60. And we have our stress is 30 times 10 raised to 6. And our area is pi over 4 of 0.5 divided by 100 squared. Sine 80 is equivalent to W, but divided by sine 60. So W here, if you calculate this one, is equivalent to 6,864.89 Newton. So again, you'll be using the smallest load so that it will be safest that the both of them can carry. So this one is too big for the wire AB to carry. So meaning to say the safest load is 579.13 Newton. Next is we have the shearing or tangential stress. So the force is oriented parallel to the surface area. The stress caused by forces acting along a parallel to the area resisting the force. So for example, we have these figures here. As you can see, we have two plates. If these are the plates and they are attached to each other, this is the bolt that is attaching them. This is what we call the, if you pull the plates in opposite direction, it will create a stress within this area. Okay? It will create a stress within the bolt. So we'll be solving for those stresses among this area. Because if you pull this one, there might be a possible stress in the middle part wherein they are um, attached to each other. We still have to use the same formula, but just do not forget to use the subscript S for the shearing stress. Okay, so this is still stress is equivalent to force over area. And area here, just don't forget the S in the stress. If it's double shear, when we say double shear, there are three plates already, which are this one, 2, and 3, which are in opposite directions alternately. You can use this formula, just multiply the area by 2. And if it's punching shear, meaning to say that still have the same formula with the shearing stress. Meaning to say kanang na ay like we are nagadukduk ka sa isa ka object and it's punching through this areas here. So that is what we call the punching shear. For example, we have here a 5 mm bolt secures two wooden planes sliding off opposite directions due to a pulling force of 25 kilonewton. What is the shearing stress applied? So when we try to draw that, so we can say that this is our planes and they are attached by a 5 mm bolt daw. So let's say this, and let's say this is the bolt that is attached by to the plane, and there is an opposite force that is acting to the plane. So kailangan nato makita ang shearing stress applied. So the same formula, we have to use stress is equivalent to F over A. So the force here is 25 kilonewton, so that's 25 times 10 cubed. And the area is the 5 mm bolt, or this is in diameter. So that is pi over 4 of 5 over 1000 squared. So the stress here is just basically equivalent to 1.28 times 10 raised to 9 Pascal or gigapascal. Okay, so this is now our final answer. Next, two plates are being pulled at opposite directions with a load of 20 kilonewton. If the plates are secured by two bolts, so there's two bolts already that is involved, 75 millimeter in diameter, what is the shearing stress applied to each bolt? So let's say this is our plane, and we have another plane, and they are attached now with two bolts. So let's say these are the two bolts that we have. There is a force acting or pulling the planes on the opposite direction. So we're looking for the stresses between the two stresses in the two bolts. So here, we'll still be using the same formula. Stress is equivalent to force over area. So for the force here, we have 20 kilonewton. However, or that's 20,000. It is divided by 2 because there's already 2 bolts that is accommodating the load or accommodating the force. So you can just divide it by 2. And then for the area, we have pi over 4. That's 75 over 1,000 squared. So basically our stress here is just equivalent to 2.26 times 10 raised to 6 Pascal, or just equivalent to 2.26 megapascal. So either, that's just the same. So for the next one, we have three plates secured by a 60 millimeter bolt are being pulled at opposite directions alternately. What pulling force is needed to shear off the bolt if it can withstand a stress of up to 175 megapascal? So if you can recall, it already includes three plates that has an opposite directions alternately. So if you can recall from here, that already involves the double shear. So we'll be applying this formula, multiply the area by 2. So we have the diameter is 60 millimeter. We have the stress, which is 175 megapascal. So we are looking for the pulling force. So when you say pulling force, that is just equivalent to F is equivalent to stress times 2A. Okay? Because that comes from F is equal to stress is equal to F over 2A. So we have the stress is 175 times 10 raised to 6. We have 2 times our area is pi over 4 times 60 over 1,000 squared. So that gives a force of 989.60 kilonewton. So this is now our force for this one. Next is what force is required to punch off a 5 millimeter hole out of a 4 millimeter thick plate if the ultimate punching stress is 200 megapascal. This was actually the same problem with your sim. So you can just answer this one. So it says here that when you say this is our plane and we'll be punching a hole, out of this one. So let's say this is the hole that will be punching out. That is said to be 5 millimeter. This is inside view. If you look at it in top view, this is the hole that will be punching out. This one, 5 millimeter. And it says that the thickness of this one is 4 millimeter. We are looking for the force that is required to punch off this 5 millimeter hole out of a 4 millimeter thick plate. So that gives us force is equivalent to stress times area. So the stress here is 200 megapascal. So that's 200 times 10 raised to 6. And the area that we are looking for here is the area or the perimeter of this one, of the thickness. So if you would roll out this area, this is rectangle. So you can just have that pi times 5 millimeter or 5 over 1000. That would be meter, and multiplied by the thickness, which is 4 millimeter. So that is just equivalent to 12.57 kilonewton. Okay, so we'll move on to the discussion of the bearing stress. Bearing stress is the contact pressure between the separate bodies. It differs from the compressive stress as it is an internal stress caused by the compressive forces. So as you can see from here, this is what we call the bearing stress, because if there's a pull of the there's a pull of some forces acting on the object, there is a bearing that is happening, or there might be a tear from our planes. Okay, so we still have to use the same formula, anti-stress, and that is in subscript B, so that we'll know that is the bearing stress, that is still equivalent to force over area. So for example, we have here, assume that a 20 millimeter diameter rivet joins the plates that are each 110 millimeter wide. So these are 110 millimeter wide. The allowable stresses are 120 megapascal for bearing in the plate material and 60 megapascal for shearing of rivet. Determine the minimum thickness of each plate, and B, the largest average tensile stress in the plates. And again, we have the given 20 millimeter diameter of the rivet. Okay, so we'll be solving for letter A. We'll be solving for the thickness of the plate. So this one. How thick is this one? So from shearing, we have different stresses. We have stress of shearing and stress on bearing. So we'll be solving for the shearing. Stress is equivalent to force over area. And from this one, we'll be using the shearing stress. So in order for us to find the thickness for the area, we have to solve first for the force. So that is, force is equivalent to 60 times 10 raised to 6 times the area, which includes the 20 millimeter diameter. So that is pi over 4. And that is 20 over 1000. squared. So the force here is equivalent to 6,000 pi Newton. But that is for the force. So from bearing, in order for us to get the thickness, can use the bearing equation. So the same equation, still we have force over area. And we will be isolating the A since that is where we will be getting the T or the thickness. So we have F over stress. And the F, as we know, is 6,000 pi Newton. And the stress for the bearing is 120 times 10 raised to 6 Pascal. And for the area, as we know, this is 20. This is the bolt is 20 millimeter. So that's 20 times the thickness. So length times width, or that's 20 over t, 20 times t. So isolating the t, we can just divide both sides by 20. So we have t is equivalent to 7.85 millimeter. Okay, that is now the thickness of our plane. Next is letter B. We have to find the largest average tensile stress in the planes. So in order for us to get that, we have stress is equivalent to force over area, and we are looking for the tensile stress. So meaning to say, we'll be using the formulas or the values that we have. F is 6,000 pi, and the area is 110 minus 20. This is 110 minus the 20 millimeter. So that is 110 minus 20 times 7.85, the thickness. This is the area of the rectangle. So that's length times width. So we have 7.85 in millimeter. And we'll be converting that into meter. So we have our stress, or the average stress, is 26.68 times 10 raised to 3 Pascal or kilopascal. Okay, so this is now our answer for letter B.